going to review Taylor series and the Taylor series error-bound formula. You have definitely seen Taylor series in calculus. You may or may not have seen the error-bound formula, so it might be less familiar and a little harder to wrap your head around, but we'll get to that at the end of this section on Taylor series, and we'll spend a little more time on it if needed. So a Taylor series is, informally we can say a Taylor series is a way to approximate a nice function, so nothing like too crazy with cusps and other things. So a nice function using a polynomial instead of using the original function. And the reason that we care about doing this sort of thing is that a polynomial is a much easier function to deal with. Your computer knows how to process a polynomial, it knows how to exponentiate, the x values and so on and so forth. But if your function is, involves a lot of different expressions that are harder to calculate, maybe exponentials, sine functions, other trigonometric things or trickier functions, it would take longer. So the polynomials can be very useful in some cases. So the Taylor series, more formally, centered at the point x equals alpha, the Taylor series centered at the point x equals alpha is going to be a polynomial, and it's going to match the function exactly at the point alpha. And then as it moves away from alpha, the series might diverge a little bit from the actual function. So the function will be matched most closely by the Taylor series at the point alpha and in the area immediately around it. So the definition of the Taylor series is the sum from n equals 0 to infinity of the nth derivative of the function evaluated at alpha over n factorial times x minus alpha to the nth power. And sometimes we will write this as the sum from n equals 0 to infinity of Cn x minus alpha to the n. And all we're doing here is renaming, the constant f, the nth derivative of f at alpha over n factorial. We're just renaming that to c sub n to make it a little easier to read and maybe notationally easier in some cases, not always. So that's the general formula for a Taylor series. Obviously, in a course like numerical methods, since we're using computers, you're not going to differentiate a series infinitely. But even if you take the sum from n equals 0 to some large number, your Taylor series is going to match the function pretty closely. And as long as we can get the function to be modeled closely enough for whatever our purposes are, we're good. We don't have to carry the calculations out to infinity. The next definition that we have here is the definition for Maclaurin series. So the Maclaurin series is exactly the same thing as the Taylor series, where alpha, the point that you expand about, is just 0. So it's the same formula as above for the Taylor series, just with 0 in place of the alpha. So we have the sum from n equals 0 to infinity of the nth derivative of f evaluated at 0 over n factorial times x to the n. And then again, we can call the constant part, the nth derivative of the function evaluated at 0 over n factorial. We can just refer to that as c sub n to make our notation easier. Now we're going to work out the example in the notes, which asks us to compute the Taylor series for the function f of x equals e to the x, centered at the point x equals 101. So in other words, this means that our alpha is 101. I would encourage you to pause this video and try to work this out on your own. and then go ahead and check whether or not your solution matches what I show in the video. As a quick comment before you start working out the solution, just know that there aren't a lot of steps in this solution. It should just be, maybe half of a page to a page at most. So if you start writing more than that, check yourself and maybe come back and look at the solution. So this would be a good time to pause. And now I'm going to go over the solution. Hopefully you paused this and worked it out before this. So the first thing to notice is we picked an easy function to do a Taylor series for. We have e to the x, and we know that the derivative of e to the x is just e to the x. So really, the nth derivative of our function, the nth derivative of e to the x, is also just going to be e to the x throughout. So if we take our Taylor series formula, which was the sum from n equals 0 to infinity of the nth derivative of alpha over n factorial times x minus alpha to the n, we can now replace our function or our derivatives with e to the alpha. That's just the derivative evaluated at alpha. So we end up with a slightly simplified series of the sum from n equals 0 to infinity of e to the alpha over n factorial times x minus alpha to the n. Now last, we know that alpha is 101 because we're centering around x equals 101. So if we plug that in, our final answer is the sum from n equals 0 to infinity of e to the 101 over n factorial times x minus 101 to the n, not to the end. And that's your answer. You should not simplify that. Obviously, computing things like x minus 101 to the n is going to get messy. And e to the 101 is going to be a very large number. So a note on this example, it's a bad example in some sense. It's a good example because having the 101 in there encourages you to not try to simplify this too much, work out, e to the 101 because you're going to get very large numbers. However, in reality, we would pretty much never expand our series around something like 101 unless we had a really good reason to need to do so. Because realistically, we want to model our functions, something like, e to the x, and we want to model it with something that our computer can work with more simply. Obviously, e to the 101 is not very simple for our computer to work with. So realistically, expanding this Taylor series around x equals 0, which is the Maclaurin series, would make a lot more sense. But I did 101 in this example to illustrate, how we would do it, and also illustrate that we would leave the final answer in this non-simplified form of e to the 101 over n factorial x minus 101 to the n, because we don't want to write a really messy expression.